Okay, so the concept of linear approximation is that we can use the equation of a tangent line to approximate values of a function near the point of tangency. All right, so just let's read what this says. It says, if a curve is locally linear, okay, we can zoom in enough and it appears to be linear. So we did that with our sine curve, where we were zooming in on the curve and we were recognizing that the sine curve, which is this red curve here, looked exactly like the equation of its tangent line, which is right here. So my sine curve was f of x equals sine x, right? And my tangent line at the origin was y equals x. And we can see that when we zoom in, that near the point of tangency, which was x equals 0, that the graphs are really, really similar to each other, right? You see how close these values all are? And it's not a great thing as you get away from the point of tangency, right? If you move this way, then these values get really, really far. There's a gap between them. Same thing down here. But near this point of tangency, those are really, really, really good approximations to our value of the sine curve, right? And I know sine of 0 is 0. I know that sine of pi over 2, that's up here, that's 1. So I know these values. I know sine of pi over 4. I know sine of pi over 3. I know sine of pi over 6. But if you ask me for what sine of 0.1 is, I would tell you I have no idea. Okay, and it's something that we just can't calculate without a calculator. And if you guys think about the technology that we've had has only been, to find sine of 0.1 on technology in the last, I don't know, like 50 years. What did they do before that? So this is what they did. They found approximation techniques so that they could come up with values, and then they tried to improve on those techniques. Same case. So I can find any value on y equals x. I can, whatever the x coordinate is, that's the y coordinate. So on y equals x, if I plug in 0.1, y of 0.1 is 0.1. That means that sine of 0.1, because I'm talking about the tangent line close to 0.1 on the sine graph, would be approximately 0.1. Okay, and it turns out this is a really good approximation because the true value of sine of 0.1 is 0.0998. All right, so we're talking like we're right in this little zone right here when we do this approximation, and they're so close to each other. They're only 2 10,000ths of a unit apart, which is a pretty impressive approximation. Okay, so that's what I mean, that when we zoom in and our curve appears to be linear, then we call it locally linear. And the whole thing about that is that we cannot tell the difference between our curve and its tangent line. So sometimes it's difficult to determine the value of a function at a certain point, especially without a calculator, but it is almost always easy to determine a y value when given a linear equation. So if we always find a linear equation, the tangent line, to approximate values of the curve near the point of tangency, it's called a linear approximation. There is a formula in your textbook for this. I don't know why. There's no reason to have a formula for this. It's using the equation of the tangent line. So to find a linearization, you're going to find the equation of the tangent line. Okay, so we're going to find the equation of the tangent line. Just as a reminder, we do that by finding the point and a slope. And y minus y1 equals m times x minus x1. The next thing is going to be to relabel it, and this is an optional step, to be honest with you. Okay, so we can relabel it as L of x, so that it says this is my linearization. And your last step is just going to be to plug in to approximate values of your function if you're asked to do so. Okay, you're not always asked to do so. So let's do a problem together. Okay, so here we have f of x equals the square root of 1 plus x, and I'm saying to do it at x equals 0, that means that my point of tangency should be x equals 0. Okay, and I want to talk about what that means. Why am I doing 0? Well, if I find f of 0, it's an easy value to evaluate. F of 0 would be square root of 1 plus 0, which is square root of 1, which is just 1. Okay, that's a really nice number. However, if I plug in a half, f of a half would be the square root of 1 plus a half, which is square root of 1.5. I have no idea what the value of the square root of 1.5 is. That's like no clue whatsoever. I need a calculator to do that. Okay, I know it's a little bit bigger than 1. How much bigger? Not a clue. I've got no basis. I've got no help. I've got nothing. So what we're going to do is we're going to find the equation of the tangent line at x equals 0. So two things. I need a point and a slope. My point I've actually just kind of found up here. So when I plug in 0, I get 1. That's actually my y-intercept, which is wonderfully convenient. To find the slope of it, I have to find the derivative. So the derivative of this function, square root of 1 plus x, is 1 over twice the square root of the same function, times literally inside is just a 1. Okay, I want the slope at the point of tangency. The point of tangency is still 0, so I'm doing f prime of 0. Now, when you're plugging in to both the function and the derivative with your point of tangency, it should be an easy plug-in. If it's requiring a calculator to evaluate either of these steps, you're not doing it right. It should be, the whole point is that this part of the process can be done without a calculator. So here I get a half. Okay, so I have a slope of a half, a y-intercept of 1. The equation of that line is y equals mx plus b. And like I said, if you want to, you can relabel it L of x so you can tell the difference between them. Okay, that's my linearization. All right, what that means is that we've, on the graph of the square root of 1 plus x, which is the green graph here, okay, the tangent line at x equals 0 is the purple line there, okay? And we can see if I wanted to plug in a half, which would be up over here, we can see that the equation of the tangent line is very, very close to the true value. So the purple value is very close to the green value. So if I can plug in to approximate square root of 1.5 here into this line, it'll be easy for me to plug in, but it'll also be pretty accurate. Okay, so now the whole point, right, well, I told you specifically to approximate f of 1.5, f of 0.5, which if I plug in 0.5, I get the square root of 1.5. You're going to see that sometimes the number that you want to approximate is the number that you're actually plugging in at this point, and sometimes it's going to be a little different. You kind of have to judge based on what kind of equation you have. If your original function is a composite, sometimes your x value is going to be a little bit different than what you might instinctually think. But if I want to approximate the square root of 1.5, I'm going to plug in to my tangent line. So I'm going to approximate this by putting in 0.5 into my tangent line approximation. Again, it's 0.5 because my original function is square root of 1 plus x. Okay, so if it's square root of 1 plus x and I want to approximate square root of 1.5, I can only plug in 0.5 for x. So that's why I'm plugging in 0.5 for x. All right, so I would do 1/2 times 1/2 plus 1, which is going to be 1.25. Okay, and that's my approximation. That's the purple value up there. Okay, so it's not always important to note this, but it's kind of interesting. The true value of square root of 1.5 is 1.224. Okay, so you're really not off by that much, and you could see it on the graph as well. Now, is it necessary to graph every single one of these? No. Okay, but it's nice to see what it is that we're doing. I do want to take a second to notice that it is an over approximation. I could see that both between these two values, but I could also see it graphically, that the purple tangent line is above the green function, and so it's an over approximation. Okay, so this situation gives me an over approximation to my value. My question is, when is that going to be true and when is it not? Okay, so there's something about the shape of the graph that makes this an over approximation. Okay, and I want you to think about it, so pause it. Think about what about the shape of the graph makes it an over approximation, and how could I change the shape of the graph to make it an under approximation? Again, what with the shape of the graph, why, based on the shape of the graph, is it an over approximation, and how could I change the shape of the graph to make it an under approximation? Think about that. When you have an answer, we'll pause it, and then when you have an answer, come back to me. All right, so this relies on concavity. So it's an over approximation when my green graph looks like this when I'm concave down. All right, so anytime my curve is concave down, the tangent lines will be above it. All right, and I'll have over approximations when I use the tangent line to approximate true values. And then when f is concave up, it'll under approximate. So if I take a curve that's concave up and I talk about the tangent lines will always be under the curve. And so if I'm using the tangent line to approximate the values of the curve, it's going to be an under approximation. Your homework is in your book. It's on page 254, numbers 1 through 6, 12, 14, and 59. I want to look at the instructions really quickly with you guys for those problems. Okay, so for this, it says to find, for 1 through 6, it says to find the linearization L of x of f of x at x equals a. So all you're doing for number 1 is finding the linearization, and the point of tangency is 2. For 2, you're finding it at -4. For 3, you're finding it at 1. Okay. And then the second thing it says is how accurate is the approximation L of a plus 0.1 to f of a plus 0.1. So for number 1, for example, you're finding the equation of the tangent line at x equals 2, and then you're going to approximate f of 2.1. So again, if you were to plug 2 into this, it's not, so f of 2 for number 1 is easy, right? It's 8 minus 4, which is 4 plus 3 is 7, easy. If I asked you for f of 2.1, you'd be like, I don't want to do that, right? 2.1 cubed is not cute. And I don't want to combine those. I'd need paper, pencil, calculator. Well, I could do paper, pencil, right, on that one. For number 2, f of -4 is easy. If I plug -4 in, I got the square root of -4 squared root of 16 plus 9 is 25. So square root of 25 is 5. F of -4 is 5. And that's what, right, that's my a value. But if I do -4 plus 0.1 to do this part, -4 plus 0.1 is -3.9. F of -3.9, I've got no clue. First of all, I don't really want to do -3.9 squared. But if I do, and I add it to 9, and I get a number a little bit less than 25, I'm not going to be able to evaluate the square root of it, which is why this linear approximation thing is super helpful. Look at number 4, for example. Natural log of 1, right? If I plug in 0, I get natural log of 1. Natural log of 1 is 0. That's easy. But if I plug in a plus 0.1, I do natural log of 1.1 then. That's like, I have no clue what that is. It's a number a little bit bigger than 0, but how much bigger? I got no idea. So you're finding the equation of the tangent line at these a values, and then the place that you're going to plug in is these a values plus 0.1. So 2.1, -3.9, 1.1, 0.1, pi plus 0.1, which is like a 3.2415 kind of thing, but you just do pi plus 0.1. And then this one would be a 0.1 again. Okay? Then on 11 through 14, you guys are going to do 12 and 14. Okay? But you're going to find a linearization, and you're going to make some choices in order to do this. So I want to look at 11 together for a second. I want to approximate square root of 101. I have no idea what square root of 101 is. I know of a number nearby that I could take the square root of easily. I know square root of 100. That's easy. That's 10. Okay, square root of 101 is a number a little bit bigger than 10, but can I be more specific? Well, using this technique, I can. So the first thing I'm going to need to figure out is a function. I have to name a function in order to figure this out. So the question is, what's the function? The second thing I need to pick is my point of tangency. Okay, so at whatever x value I'm going to do. So what function is good to approximate the square root of something? Well, how about the square root function? Square root of x. Right, that would work. Okay, where is close to 101? Well, we just said it. That's easy to evaluate, is 100. So I could do that. Okay, now I'm not locked into this. Okay, I can probably write a million different functions. I could probably write infinitely many different functions. I could do the square root of x plus 100 and make that my function. Where would I find its point of tangency then? Well, again, I have to relate it to something that's an easy number to evaluate, that's close to the number that I want. So I want the square root of 101. Square root of 100 is nice, so I could do this second equation at x equals 0. There's a bunch of different ways that you could write this. I would stick to simple, which is not this, it's this. So think about that as we move through.